Good afternoon, everybody, and welcome to the 3:30 talk in the market share track. This is Windows 7 internals and exploitability. A couple reminders before we get started. Please silence your cell phones. And then in your package, you should have gotten speaker feedback forms. Please take some time after the talk, fill them out, and turn them in at the information booth. It'd be very appreciated. And with that, here's Sukasa.
Hi. Now I'm going to talk about Windows Phone 7 operating system and its security. I personally think this is a bit out of date. Shame on me. Anyway, here's the agenda. The main topic is Windows Phone 7 operating system. I describe internals of this OS in overview and also describe possibilities of exploitation. I have used some tools and techniques to analyze the system, and I will also talk about reverse engineering of Windows Phone 7. So let's get started. First, I need to talk about Windows Phone 7 overview. Windows Phone 7 is the operating system developed by Microsoft. This operating system is based on Windows CE 6, and it looks some special components ported from Windows Evident Compact 7. One of the features of Windows Phone 7 is strong security. Applications are sandboxes in order to protect system and user together. And each applications are separated using capabilities and chambers, which makes accessing unauthorized resources nearly impossible. More interestingly, normal Windows Phone 7 applications are not authorized to use native code. Only .NET code is allowed. Well, native code could be exploitable. So, this is the format of Windows Phone application package. It's very similar to Silverlight's one. In fact, Windows Phone package is a Silverlight package with a few extensions. The main difference is WM app manifest.xml. It's similar to Android manifest.xml and declares app metadata such as ID and version information and capability information I describe later. This is the end for normal applications, but some privileged applications have native code, which is interestingly. Those application packages have native code DLL and wp-manifest.xml, which indicates existence of native code. Well, let's look at the security. Windows Phone 7 manifest declares capabilities which determines resources to be authorized to use. This is similar to Android's permission system. There are main capabilities indicating device features such as camera, microphone, sensors, and user or device identification. And more interestingly, use of special components such as web browser. So let's look at the Windows Phone Marketplace website. This is the description page for Facebook app. In this page, you will see app will use location services, data services, blah, 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 blah. This indicates and notifies what resources the app uses, just like Android. One thing I'm a bit worrying is there's no confirmation like Android when you install the application. Instead, Windows Phone application are completely separated, and unlike Android, there's resources are managed by capabilities very strictly. There's more. Most of capabilities are documented and authorized to use by normal developers. However, there are some undocumented capabilities which enable higher privileges. For instance, ID cap interrupt services permits access to third-party services. This is very interesting, so I will talk about this later. Anyway, let's move on for now. Chambers. These features isolates applications drivers by separate chambers and separate policies. The most important part of this security policy and security model is the TCB, stands for Trusted Computing Base, which kernel and some drivers reside. Normal applications are isolated at LPC, least privileged chamber, which has very low privileges. And pure chamber model is good for security, but not so flexible. So Windows Phone 7 gives additional permissions declared by capabilities. This will secure the device and keep application model flexible. In conclusion, these security features looks modern, secure, well designed. It looks great. So only thing we need is to know how good they are. We need to analyze the system if we want to know how good they are. So I will talk about the system, low-layer implementation. Most of modern operating systems, including Windows Phone 7, have features for exploit mitigation, which makes arbitrary code, which prevents arbitrary code execution. I have started to analyze the system from this low-layer implementation here. So I have to describe how I analyze the system. Well, I used unlocked Windows Phone device. Mainly, I used HCC 7 Mozart, and I used undocumented features to learn native code. So I made custom DLL to analyze the system. Interestingly, native DLL for Windows Phone 7 can be created using SDK for Windows Mobile 6. And, of course, I used reverse engineering techniques. I will talk about reverse engineering later. It's fun. So let's get started from process memory. So the layer looks very similar to Windows CE 6. There's 1 gigabyte of user VM instead of 2 gigabytes of normal Windows NT. And shared DLL and mapped file areas are located on higher memory areas. Unlike Windows CE 4.2, which is used by Windows Mobile 6, all processes are properly separated, just like Windows NT. This is pretty good. So I use native code to generate memory map, and it seems DP, data execution prevention, is working quite well. Well, I however discovered an application issue. Well, I will talk about this in exploitation part. There's one more memory-based exploit mitigation feature, SLR. This feature randomizes memory addresses used in the program and makes predicting specific code addresses and exploiting them much harder. Looking at the layout, the most of the layout areas are randomized. So let's see some details. Stack, executable image, heap, virtual memory addresses are all randomized every time you launch the application. Very good. Shared DLLs, which include common native DLLs, and memory mapped files area, which include common .NET assemblies are also randomized. They are randomized every time you boot the device. This is not ideal, but it's enough. And there's more. Normally, operating systems for ARM architectures uses SWI instruction to make system calls. However, Windows Phone 7 uses completely different way to make system call. In this operating system, the PSL calls. The program makes PSL calls by making a branch to specific address. These addresses are called trap addresses, and making branch to them we call trap, exception. If the exception handler catches the PSL call, it redirects to the PSL handler, and which could be a kernel mode function, or it could be a user mode callback. And the thing is, predicting trap addresses will make exploitation much easier. Fortunately, Microsoft had done well. In Windows Phone 7 and latest versions of Windows CE, the actual trap addresses are randomized by PSL trap seed, which is a part of kernel shared memory called user kdata, similar to Windows shared user data. This makes exploitation and running system calls in Windows Phone much harder. Let's see the disassembly. This is the disassembly in core DL and making system call of AMAP view of file in process. Okay, 0x F101 FFO is base trap address of AMAP view of file. But this is not used directly. You see, PSL trap seed is loaded here, and the trap address is randomized, XORed using PSL trap seed, and then made branch here. Pretty cool. So in conclusion, I discovered almost all process memory areas are randomized. This is pretty good. However, I have also discovered something worrying to me. It's the allocation pattern. For instance, Linux mmap system calls makes random gap between two allocations, which significantly increases the strength of ASLR. However, Windows Phone 7's implementation doesn't do so. So it makes heap spray or similar techniques much easier and more reliable. That's worrying. But there's more security system. Applications sandbox, and it seems hard to take over the system. This security feature is related to 2 or 3 components. The main components are policy engine and security loader. All resource accesses are enforced by the policy engine, policyengine.drl. Also, this engine isolates applications and denies unauthorized accesses. Actual policy data is contained in the policy database in specific location, but we can see the policy data by viewing policy XML file, which is located in /windows/basepolicy.xml. So let's see this file. Okay. Okay, that's this is a base policy.xml extracted from the device. It's quite readable by humans. And more interestingly, there are many comments to describe how policy does. And it makes understanding the policy much easier. Well, looking at the policy, I cannot find any critical design flaw. This policy conforms the principle of least privilege, and exploiting system seems difficult for now. So let's move on. There's one more. The security loader verifies executables and modules before you run the applications and load the module. This security loader, LVMod, only allows modules contained in the ROM and modules signed by Microsoft. For instance, all Windows Phone Marketplace files are signed by Microsoft. This is how Windows Phone Marketplace files actually works. This is good for security, but not good for application developers. So there's also a feature called Developer Unlock. This feature authorizes a limited number of unsigned applications running according to specific registry value. Well, this security loader looks similar to Apple's iOS, but unlike that, there's no signatures required for memory pages. In other words, executable memory areas are simply executable, not need to be signed by Apple or something. In conclusion, I can say this design seems good. There are some issues actually, but it looks not critical for now. So let's move on to the next one, reverse engineering. It's fun, okay? Yeah. Unfortunately, Windows Phone 7 details are undocumented, and it seems black box, but not. Actually, it's not. It's not black box, and we can use reverse engineering techniques for Windows CE. Also, it seems you can reverse Windows Phone 7, even you don't own the device, actually. Of course, there's some obstacles for reverse engineering, but they can be cleared easily. So I have made simple collection of Python scripts named W7 helper tools to make analysis easier. I have missed the tools in conference CD, but it will be available in Blackhat archives page. So, and most of all, reverse engineering of this operating system is not so difficult. So let's do it. So, the first step to reverse engineering is retrieving files. If you need to analyze all system, you will need OS image. Fortunately, some OEMs like HTC made recovery image available. Also, their web-based updater files can be used. These updater files are available for download from Microsoft website and can be extracted as a CAP archive. However, they are not ordinary PE files, and it will not correctly analyze in IDEA Pro. So we have to convert it and fix it before using IDEA Pro. So, OS image. If you have OS image, you can use XIDump or similar ROM extraction tools available from XDA developers' website. These tools will extract all the files contained in the image. But this is not the end. The dump generated by XIDump or similar tools has special format. This is because Windows CE ROM contains PE files in specific format, XIB, not PE. So I made simple script unpack-xib.py to convert XIB to PE from, If you have web-based updated files, you can extract the file twice. This is because the CAB file contains one or more package files, which actually CAB archives. I will show you. So I already unpacked the actual updated CAB file, and there are many package file, extension PKG, but it's actually a CAB archive, so you can extract easily. So let's look at the folder here. Well, it contains PE file, actually. But this is not enough, because these PE files are not aligned properly, and some part of headers are corrupted. So we have to fix the file using unpack-updated.py. This tool realigns and fixes the PE file to make RDA Pro analyze the file correctly. Talking of correctness, we need to care about version of IDEA Pro, because earlier version of IDEA Pro had an analysis issue under Windows Phone 7 modules. Well, looking at the disassembly, it's very clear. The function ends in the first instruction. This is not supposed to happen. It's not good. I discovered why. IDEA Pro did not correctly handle function table. More specifically, the LSB or begin address of the function. So I added an option to avoid this issue, and it will make analysis much better. I also reported this issue to Hextrace, and it's fixed in IDEA Pro 6.3. Effects by fixing the files, it's very clear. Before you use the specific option, you will see the red areas which indicates code but not function. But after you fix the files, you will see almost everything blue, the code, and code is in the function. It makes analysis almost correct. There's more. You will use symbol files to analyze Windows NT. So how about symbols in Windows Phone? Well, I found debug directory in here, and interestingly, simple. You can actually retrieve PDB files from well-known Microsoft symbol files. W7 helper tools have an option to fix debug directory and load PDB file. That's all. And there's one more thing to note about. If you load the PDB file before you analyze the file, IDEA Pro won't analyze the file correctly. And this is an issue too. So there's a tip. We need to analyze the file, then load the PDB file. Still, loading PDB files may corrupt the analysis, so I use simple IDEA Python to automate fix process. Well, let's see this in the demo. So I will start analyzing Pacman client.dll, which is a part of package manager in Windows Phone. Sorry? Oh, that's good. Okay. Pacman client.dll. So let's start analysis. First, choose the processor type, ARM, and edit architecture options to select ARM v7A and ARM. Okay, that works. So IDA Pro asks input files has symbol, and well, this is quite interesting, but answer is no, because this may corrupt the analysis. No here. Okay, analyze. So I enter a simple IDA person here to collect all sum-based function. Done. So I have recorded the all sum function to prevent corrupted analysis. Then you can choose options here and disable or automated analysis temporarily. Then load the PDB file. Well, this makes analysis has just collapsed. So let's fix this. Okay, that's fixed. So I have fixed the actual function, so I can re-enable the analysis and reanalyze the program. Perfect. Well, as you can see, there's many symbols available here. As you can see, Pacman client implemented in C++. Pretty good. Well, that's all. As I showed, reverse engineering Windows 7 is not so difficult. You could analyze everything in operating system. Thanks. So this is the end of reverse engineering part, and now the exploitation part. So native components have been always targeted for arbitrary code execution, and we need to know what is exploitable. There are several possibilities. One, Microsoft components such as .NET, Core Library, and Internet Explorer. Two, third-party components, which include OEM drivers, 3. Native code in third-party applications. Well, here's some observations. One of them was memory in .NET. That was disappointing. I found strings generated and dynamically allocated strings are located in the user VM, which access is R, W, and X. In other words, dynamic strings are executable. It could lead to string technique if there are other vulnerabilities here. And if the attacker can spray executable code as Unicode strings and control PC program counter using native vulnerability, it's possible they execute dynamic string inside the process. The exploitation attacking native components using native .NET might be possible. The next one is native code in third-party applications. Unfortunately, or fortunately, there's very few apps using native code. According to a Japanese website, there were 48 applications using native code. Most of them were used by OEMs or carriers, but there are some non-OEM applications which include Adobe Reader and Tango video calls. So I wonder, is native code vulnerable? Let's move on. In order to find such vulnerabilities, there are several ways like static analysis using IDA Pro or using fuzzing. I completely agree with this. And I have planned to do so until I find this. Well, you see that? This is the strings window of IDA Pro, and the string says inflate 1.2.1 copyright 1995-2003 MAC address. Well, it's the signature of old and vulnerable zlib. Well, unfortunately, I cannot disclose what application had, but I think I can describe this vulnerability because it's existing one. Sorry. This vulnerability is number CVE 2005-2096. 2005, you know? This is the buffer overflow vulnerability in zlib before version 1.2.3. The characteristics and exploitability of this vulnerability will change according to the alloc function, which is set by every application. Actually, it was heap overflow, which destroyed heap managed by local alloc. As a result, it will result in crash. Well, fortunately, the attacker could overwrite the memory, but attacker cannot control the content of overwrite. So I think it's not possible to execute arbitrary code in this using this vulnerability. And I also could not find critical vulnerability which allows arbitrary code execution. But, well, it seems hopeful, isn't it? So, post-exploitation part. So we assume the attacker can execute arbitrary code in some applications, but applications are isolated, and most of them have least privilege. So just exploiting one vulnerability is not enough. The attacker has to get higher privileges to do something more interesting for attackers. So I looked for possibilities of previous escalation, and I found this undocumented capabilities, ID cap interrupt services. I think this is a design flaw by Microsoft. This capability, ID cap interrupt services, allows access to third-party services, interrupt services. I thought this capability is used just for OEM applications, but this is actually used by non-OEM apps, such as Tango video calls. I discovered Tango video calls have to modify specific registry value, but it could also lead in previous escalations. Why? Simple. Well, some OEM drivers could be vulnerable, and actually vulnerable. I have actually no good feelings about OEM drivers or interfaces because I and many hackers have found several routing or critical security vulnerabilities in OEM drivers, interfaces, customizations in Android devices, many Android devices. I have seen several OEM interfaces which could be vulnerable or could allow too much resource accesses. So this is a sketch of escaping chambers. If ID cap interrupt services apps are compromised, such as Tango video calls is compromised, the attacker can access to interrupt services. Some interrupt services are poorly designed and will allow resources in other applications, and the attacker will steal information, modify system, blah, 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 blah. Even looking at the demo device, which is HTC 7 Mozart, the result was no good. There are privileged interfaces to access file system, registry value, and more of that, raw memory. Some interfaces are disabled or restricted in later versions, but still, improper access vector remains. There are some vulnerabilities. Well, I have planned to demonstrate this, but, well, I accidentally broke the demo environment, so I think only thing I can do is show the file stolen from the OEM interfaces. So, stored VOL file. This is used by Outlook applications, and it contains, well, frankly, very useful information. For instance, I have assigned the Gmail address to the Windows Phone device. So let's search for Gmail. Here, oi.tsukasa.ffr@gmail.com. Here appears the email address. Also, you can see the sender of the mail, and look at some, well, see it? No. Oh. There's a message information. I have attached sample4.bin. It could also show. Actual sample4.bin is located at same Outlook store directory, and I can steal the data as well. conclusion, Windows Phone 7 is mostly designed secure. However, some OEM components drivers seem to be unconcerned about security, and Microsoft allowed OEMs to use one capabilities, ID cap interrupt services. I think capability separation is very important. Microsoft should have been separated OEM capabilities correctly, and Microsoft should control OEM capability and its security. So I have described Windows Phone 7 internals and some possibility of exploitation. So let's move on to the conclusion. Here. So, sandbox and application systems design secure, conforming principle of least privilege. This is good, but and native code exploitation. Operating system is designed well, but some concerns here regarding insufficient ASLR and .NET memory. And more of that, if the app with ICAP interrupt services capability is vulnerable, it may result in sandbox bypass. So, in general conclusion, Windows Phone 7.x implements very strong sandbox. However, there are some concerns here, specifically interrupt services, OEM interfaces, and native code could be a design failure, design flaw. It has to be fixed in Windows Phone 8, and I guess it will. Well, Microsoft has recently announced Windows Phone 8 operating system and announced Windows Phone 8 uses shared Windows core, same as Windows 8. So it means anti-kernels is coming to Windows Phone 8. Anti-kernels implements proper mitigation feature or advanced feature. So I expecting strong memory protection and exploit mitigation. And more of that, Windows Phone 8 allows native code access in default. So it will minimize ID cap interrupt services attack surface because those applications will no longer require to use such privileges. This is good news for us, so I have to say congrats Microsoft. So this is the end of the presentation. And do you have any questions? Well, I'm